All right, first thing we're doing today is the bell ringer. And the bell ringer, I put a pendulum up with a length of 55 centimeters. And I said I pulled it back 10 centimeters from equilibrium. And the question is, where is it? Where is the object in 2 seconds? That's what they're trying to work on right now. I apologize for those of you watching the video. There is a good amount of today that is going to be like visual in class. I don't necessarily know how to do the camera very well quickly, so I'll see what I can do for you.
And you said after 2 seconds?
After 2 seconds, where?
Amplitude is 10, so 10 like a little sign. Wait, mode, ratings.
All right, I'm going to get going here. I know there's not quite enough time, but if you want to not pay attention, that's fine. But also, let's talk just very generically here. Again, I mentioned this yesterday. This is the kinematics of simple harmonic motion. And I said yesterday, but I'll repeat myself, essentially kinematics was give me some starting information. Like I start from rest, and I accelerate at 3 meters per second squared. And then all you need is, all right, cool. I got those starting 2 pieces of information. Tell me when you want to know, and I'll tell you exactly where it is, right? And in a way, kinematics is much more complicated because the possible options of where the object ends up is anywhere in space. It could be, 2 meters away. It could be 90 million meters away, and all of it would necessarily work. When we are doing this, ultimately, your answer has to be somewhere in there. So I said I pulled it back 10 centimeters in that direction, right? So it's either 10 centimeters that way from equilibrium, or it's 10 centimeters this way from equilibrium, right? That's it. Now, we talked yesterday about kind of starting to split this sort of up into fourths. Think about this kind of in sections of a quarter of the way through. Like a quarter of the way through, it's going to be at equilibrium. Another quarter of the way through, it's going to be at the negative amplitude, and then vice versa. The third quarter is going to go back to equilibrium, and the fourth quarter is going to go back to where it started, right? So in a very generic way, the moment you figure out that the period is even before you calculate the period, you could have literally done this. Most of you guys are so used to calculating that you didn't do the very simplest thing, and that is just this. I was pulling it back and forth the entire time. Meaning you could have just taken a timer and gone, click, 2 seconds. It's right there. That's what you could have done, right? Obviously you didn't. That's fine. So many of you calculated period, which we've said a couple times. What is it? 1.48, 1.49, somewhere in that range. I'm going to say 1.48 is what I calculated earlier. It's what I remember from first hour, so I'm consistent. So what does that mean? Well, in 2 seconds, it's definitely completed 1 cycle, right? Yeah. So that means what we kind of got to figure out is how much is left over. 0.52 is now left over to finish, right? Just taking the leftover bit. Is that more than a fourth? Yes. Right. Is that more than a half? No. Which means it's in the second quarter, right? So generically, here's what happened. It went that way and back in 1.48 seconds, and then it came down here in 1 quarter, and it's somewhere over here. Does that make sense? So it's on that side, on its way out to that. That's ultimately what the answer is. Does that make sense? Okay. Now, we're going to get into the math. That's great today. But ultimately, I don't want you to lose that simplistic thing of what you just did. Hey, I know the total time. I could very easily just kind of like roughly work out where it's going to be. Cool beans? Cool beans. All right, so I'm going to put up the calculation that pretty much all of you did for the sake of posterity. 2 pi times the square root of length over g. So 2 pi times the square root of 0.55 meters divided by g. Why does it have to be in meters? Yeah, that's it. That's the only reason. Yeah, if the units matched, then it would not have to be in meters. But since gravity is in meters, that's why. You are more than welcome to change gravity to 980 centimeters per second squared if you prefer, and leave it as 55, and of course it'll get you the same thing. And you ended up with 1.48 seconds. All right, what is my next step? Well, I will tell you the technical next step, but I'm going to make kind of a pretty large aside to talk about this. The next step is calculating this. 2 pi over T, that angular frequency, but that was a weird conversation at the end of yesterday. So I want to spend a little bit more time on that real quick before we come back and finish this problem. All right. The first thing I need to address with you is frequency. So I'm going to make up a new number for a new problem. It's nothing to do with it. We'll go back, kind of a quick aside here. Let's say that the period is 2 seconds. Okay, and it takes 2 seconds for something to go back and forth. I don't know if we did this one. That is actually that's a grandfather clock. Okay, a pendulum with a length of, that's actually what this was designed for. A pendulum with a length of 1 meter has a period of 2 seconds. And so a grandfather clock uses a pendulum like that, and it doesn't actually use the period, it uses half the period. And tick, tock, 1 second, 2 second, 3 second, 4. This conversation is now taking 10 seconds. All right, that's what it is. So that's to give you a visual representation. That system would take 2 seconds. Let's talk frequency for a second. Okay, frequency is the exact same freaking measurement as period. Frequency only exists because humans hate fractions. That's it. That is literally it. Frequency, by definition, is the inverse of period. Remind me what period is again?
How long it takes to go through a full cycle?
So technically, the units on this would be second per cycle, right? And we don't usually use cycles, so we just say seconds, but we all know it's there, correct?
Yeah.
So then, technically, what numerically would be the inverse of this period? What's that? What would the number be? Yeah, you got it. You get the next question. You can do this. 0.5 or 1/2, yeah. And exactly like you said, that's cycles per second. But as I just mentioned, we don't usually ever write cycles. So what would its official units be? Oh, come on, you're taking my 1 per second. So it's the inverse of second. But obviously the inverse of second is annoying, so we gave it a name. We gave it hertz. But when you look at hertz, it's technically 1/seconds, or even technically further, cycles per second. So what is this saying is happening? It's saying it's going to go through about 1/2 a cycle every second. Does that make sense based on that number right there? Sure, 100% it does. Now, when I'm dealing with these low numbers, you can kind of come to terms with both of those. Meaning if it takes 2 seconds to go through a full cycle, it's going to go through 1/2 a cycle in 1 second. Great. But what if numbers are different? Like what if I instead dealt with, say, time is 90 seconds? Calculate for me then, very quickly, what's the frequency of that? Yes? What does that say? That says you go through a little bit more than 1% of a cycle per second. Do they say the same thing? Yeah. It's going to take me about 90 seconds to add all this up to 1. Right? Now, that being said, I give you both of these numbers which mean the same thing. Which of these two numbers makes a lot more sense to you in terms of like easily understanding what it's trying to say?
Period.
Yeah. Absolutely period. Okay, now let me do a different one. Okay. I'm still going to do it in here. Let's say that the period of something is 0.00391 seconds, or if you prefer, 3.91 milliseconds. I'll remind you that human reaction time is roughly 1.15 seconds, which is 150 milliseconds. Or roughly speaking, this cycles through about 40 times in our human perception, okay? And if you told me 0.00391 seconds, and then you gave me another situation that added another 0, I mean, I've been doing this 16 years, and I would be like, they're both tiny numbers. I don't fully grasp. Yes? Doesn't make a ton of sense to understand. Now watch this. What's the frequency of that? Do it.
255
I'm going to round to 256. I'm specifically going to round to 256 because we're describing middle C. Middle C, when played on a note, is simply any particular instrument vibrates back and forth 256 times in 1 second. So it makes sense that it wouldn't take very long for it to cycle one time, right? Now, as you look at these two numbers, which of the two of them probably makes more sense in your brain to comprehend what it is that's happening? You don't like fractions. There it is. Why is period better in one case and frequency better in the other? They're the same measurement, it's just you don't like. Fractions you can better understand. The other ones, that's the only difference. Okay? Now, what I'm going to try to do now is take these two numbers and then compare a third number, which I think will be particularly useful for what we're going to say. So let's go back to that. No, let's say the period is a half a second. Okay? Going back and forth relatively quickly. What's the frequency of that? 2 hertz. What does that mean? It takes a half a second to go through one cycle. What does that mean? Same thing, right? Literally the same thing. They both say the exact same thing. Now, yesterday I gave you this equation, and I called it angular frequency, except you started with angular velocity, right? Angular velocity is how quickly it gets around a circle, and weirdly I called it angular frequency instead. Now, if I change this equation ever so slightly, you look at it like that. What did we literally just say that 1 over t is? So that means that equation is also 2 pi times frequency. Yes? All it is literally doing is putting frequency on a different scale. That's it. Okay? So, I'll come back to these numbers in a second. If period is 1 second, it takes 1 second to go through one cycle, right? And frequency would be 1 hertz, because it goes through one cycle every 1 second. And angular frequency would be, or 6.28 radian. This is 100%, this is 100%, this is 100%. What do I mean by this is 100%? How much angle does it take to go through a full circle? 6.28 radians. Here's a good scale to kind of think about it. 0% to 100% of a cycle. For frequency, that's just 0 cycles to 1 cycle. For angular frequency, that is just 0 radians to 6.28 radians. How are we doing, Ish? So coming back here, what would the angular frequency of this situation be? Don't leave pi in it, we need numbers. 12.56. Here's what's hard to get used to. These two numbers say the exact same thing. What does that say? It says it's going to go through 2 cycles every 1 second. What does that say? It's going to go through 12.56 radians, or if you'd like it in degrees, 720 degrees in 1 second. How many cycles is that? 2. Is that the same thing?
Yeah.
Yes. Let's try with another set of numbers that might help even more. Let's say, for example, I told you that the period of something was 4 seconds. So we're slowing it way down in this case. What would the frequency be?
25.
What does that frequency mean?
You'll go through. It took 1 second to go through 0.25 of the cycle.
We'll say that a little bit differently, but you're right there. In 1 second, you're going through about a quarter of a cycle. So how many seconds is it going to take to go through a full cycle? 4. And what would the angular frequency be? 1.57. So Let me draw the circle. How much through that circle, how much through that cycle is 1.57 radians? 25%. How are we doing? Okay, we're going to use that and we're going to go back to our original problem now. In our original problem, I said after finding period, I said we could skip immediately to angular frequency. Now you absolutely can, but it can be a little bit easier to understand if instead of going immediately to angular frequency, you actually just start with regular frequency. So what would the frequency be of this? You want to be doing these calculations, so you're just getting used to your fingers. 0.68. Or, what that says is in 1 second, it's going to go through about 68% of a cycle, right? Why? Well, how long did we say one full period is? 1.48 seconds. So 1 second is about 2/3 of that, right? Is 1 second about 2/3 of a cycle?
Yeah.
Or 0.67%, a little bit more than 2/3 of a cycle? Literally what it's saying here. So now all I'm going to do is I'm going to put angular frequency on a different scale. Okay, instead of going 0 to 1, I want to go to 0 to 6.28 by taking 68% and finding out of 2 pi, 6.28, how much of that is 68%. And what would that be? What is the angular frequency? By the way, in case you're struggling on the equations we're using, frequency was just equal to 1 over period, and angular frequency is to 2 pi times that frequency. What'd you get?
4.25.
Can confirm a couple people? Notice, by the way, the units on both of these are exactly the same because they're saying the same thing. Okay, this goes through 68% of the cycle. So does this. Let me show you why I know that. Okay, just kind of roughly remembering, here's 1 radian, here's 2 radians, here's 3 radians, here's 4 radians. So 4.25 radians is roughly about here-ish. Is that about 68% of the way through the circle? Yes, they say the same thing. To which you should ask the most amazing question, why the heck are we making this more complicated? And the answer is, so we can use this. Because what has to be put in here? Can I just put percentage into cosine and it spit out what I need? No, I have to put an angle in. So I have to know what angle is 68%. Right? So right now, if I took this calculation and I plugged in 1 second, it would tell me that the angle is 4.25. And cosine would go, great, you're about 68% of the way through the cycle. If that were the case, what it would tell me is it would go, okay, you started it over on this side. Remember I talked about splitting this into fourths? Okay, you started over here, there's 25%, there's 50% over there, 68% is right about here-ish, close to back to the middle. Is that close to about the middle there? The x value of that? Yes, literally what we're looking for in that case. So let's actually use your numbers. A was what?
0.1.
A was, actually, I'm just going to use 10 centimeters. I'll talk to you about why you can do that. If you're fine at 0.1, but actually 10 centimeters is fine here. Okay. Cosine of 4.25 hertz times 2 seconds. Now I'm going to take this piece by piece, so hopefully you try to understand. What is 4.28 times 2? 8.5. And hertz is 1 over seconds, and seconds is seconds. So what are those going to do? Cancel. And so actually we're left with radians. This is an angle. So where is 8.5? Well, 8.5 would be through 1 cycle, right? And then let's figure out how much is left over. 8.5 minus 6.28, we have A little bit left over, 2.22. And 2.22, is that more than a quarter? So that would go more than a quarter. Is it more than a half?
Yeah.
Is 2.22 more than a half? No, because half would be up 3.14. So it would be somewhere in here-ish, right? So has it gone through one cycle and then a quarter and then a little bit extra? If you go back to what we talked about at the very, very beginning, I just used the fact that the period takes 1.48 seconds to say, hey, it's going to go through one cycle, and how much do we have left over? 0.52. Is 0.52 more than a quarter? Yes. Is it more than a half? No. So it's in that second quarter right over there. And is that exactly what that says right here? Okay, so now we take the cosine of 8.5. Make sure it's in radians. Tell me what you get. Negative 0.1. Negative 0.6 what?
6.5.
So yeah. What does that say? Well, that says, number one, you're on the negative side of the equilibrium. Is that what we found? Yep. Okay. And you're 65% of the way to a full amplitude. Okay. Now, if I want to know exactly where I'm in, if I have 65%, all I got to do is multiply by the total amplitude, telling me that the position is negative 6.5 centimeters. What does that say? It says from equilibrium, go this way 6.5 centimeters, and that's where the object is at. Does that make sense-ish? Let's try it again. Now, I wanted you to understand this. I wanted to take a little bit extra time to understand these individual pieces for some, but I also recognize we're going very, very quickly, and some of you just want, I'm going to do a very mathy thing, and I'm just going to give you the steps. Okay? So if you just want the steps, I'm going to give you the steps. So we're going to do one more problem real quick, and I'm just going to go through it very quickly so that way you can write this down, and if you're stuck on the homework, for the most part, you can just look at this verbatim and pretty much cover it. So I'm going to use a spring we've used before so that we don't have to waste time on that, although usually what I would normally do with one of these problems is start you off trying to calculate K. Since we already know the K of this is 27.7, I'm going to tell it to you. But again, the first step, I'll put the steps kind of over here of what I would usually do on one of these problems. The first thing I would usually do is find K. But on this problem, I'm just going to go ahead and tell you that K is 27.7 newtons per meter. Now, instead of putting the thing I put on there the other day, I put on 150 grams. Unlike what I did a second ago, rather than start this stretched out, I'm going to start it right here at the beginning. I'm going to poke it upwards, just like that. And we'll say that it poked up about 4 centimeters. So I poked it upwards, and it went up about 4 centimeters. The question is, where is this in 2 seconds? It doesn't always have to be 2 seconds. I'm just trying to be consistent in that particular way. Now, I will also tell you this. If you would like, you kind of saw on that previous page that I've been using X versus T. My apologies, very pre-calculus here. It's almost like pre-calculus has absolutely application in the real world and we use it all the time. Not just a random set of things that they do. Anyway, X versus T is usually because I've been going left and right. Since I'm going up and down in this case, I am going to say Y versus T. It changes absolutely nothing about the setup whatsoever. As a matter of fact, if you are uncomfortable by that, if that bothers you the entire time, you can use X versus T this entire time and I won't have any issue with it. Just make sure that obviously you are talking instead of left and right, obviously up and down in this particular case. So I'm going to find K, which I already have. Once I find K, what am I probably going to do next? I'm going to go find the period, correct. And through that, so I'm just going to go T is 2 pi square root of M over K. Why does M have to be in kilograms? Because K is in newtons, correct. Someone tell me what you get. 0.46. So again, the moment I have that, I should have a pretty darn good idea of what my answer should probably be. Meaning, in 2 seconds, what's going to happen? That's going to cycle about 4 times before I ever actually care, and then there's a little bit extra, and that's where I'm going to start to try to figure out. Does that make sense? I'm going to have what, 0.04, 0.16 seconds left to try to figure out exactly where it's going to be. Now my next step with period, there are two things that can be done. I've kind of showed this on the last one. The first is you can go immediately to angular frequency by this equation right here. It's the same as angular velocity. Okay? Tells us, and what that's saying is, hey, 100% of a cycle takes this much time. But that's kind of confusing for people to understand. So oftentimes, you can go straight there. Oftentimes, the preference by a lot of students to better understand the situation is to actually start with frequency and then go to angular frequency. Now, those of you astute viewers, notice if you substitute that guy in right there, it's the exact same equation we started with a second ago. I'm just splitting it into pieces to better understand. So this is what I'm going to do here. What is frequency?
13 points.
No, frequency, not angular frequency. You stepped ahead of me there. You're all right. 2.7 what? 17. That makes more sense. 2.17 hertz. So what does that equate? What does that guy say?
You go through 2 cycles and a little extra every.
Does that make sense given the period?
Yeah.
Cool beans. Next, you already were telling it a second ago, so angular frequency should be 2 pi times that 2.17 hertz. What do you get?
13.6.
13.6. Yeah, okay. With some change, but there we go. 16.6 hertz. Does that say the same thing? Yes. It says it's going to go through 6.28. Then it's going to go through 12.56. And it's got a little bit extra. It's got a little bit extra. They say the exact same things. So the next step after finding period is to go to frequency / angular frequency. From there, now we can go to that equation that we've been using. But I'm going to do this, y sub t. I'm just going to do the generic equation first. The generic equation is one that just doesn't worry about any constants yet. So I'm going to call this A, and here's the deal. Why do I have to worry about this? Well, Spainhour said he is starting right here and poking upwards. Should we be using cosine? No, we should not. Okay? As a matter of fact, I did something on the last problem without kind of telling you. My apologies. On the last problem, I did something that you should not do on a problem, and that is make an assumption without telling you what it is. What assumption did I make at the very beginning of this problem? The direction of positive. Which did I assume the direction of positive was?
Right.
Right where I started, correct. Which is correct to give us cosine. You should always establish that. Had I said that way is positive, teaser, what would we technically have done? Got negative, yeah, absolutely. So, in this case, we should probably begin by establishing positive before we try to. I'm just giving you a hard time. You're completely lying. It's because you make that face that we do it. All right, which way do you want to be positive? Up. I like it. So since you've said up is positive, just to kind of give you this real quick, you're starting at equilibrium and you're going positive. First, what trig function are you using? Sine. So this is the general equation. There's your general equation. And the general equation, again, is just that without any constants. So let's start now filling in those actual constants. What should amplitude be? 4 centimeters. Why do I not have to make that meters? I keep asking you why I have to make something kilograms, why I have to make something meters. Why don't I have to make that into meters?
Because the units all cancel the radians.
Not quite what I'm looking for. I think you're in this general vicinity. The output of sine is a percentage, right? It's just a percentage. What percentage of centimeters right here? I mean, and in that vein, Kenzie, you're 100% right. The units all cancel, so there are really it's unitless over here. So we can leave it at percentage of centimeters, or if you want to put it in meters, that's completely fine. What's up? Sure. I don't want to talk to you right now. Okay. All right. So, sine of what's angular velocity? Or angular frequency? Sine of 13.6 hertz times what? 2 seconds. So now you're going to multiply that out and you're going to get 27.2. What is that 27.2 doing in there? It's saying the exact same thing we knew already. That's such a big number because it's going to go around 6.28. Now it's going to go 12.56. Then it's going to go through another 12.56 for the other 4 cycles to end up with about 13.12. 13.12 would be, did I do that right? No. 20. I'm doing math somewhere dumb in my head. 23 something. It's about 4 cycles and something extra, which is literally what we've said is going to happen here. This is going to look at the extra and spit out an answer. What do you get? What do you get for this piece right here? Just the sine part.
Just the sine?
Just the sine part.
0.88.
0.88. So that says, of course, that it's in the positive direction 88% of the way up to the amplitude. So now we just multiply by 4 centimeters to get exactly where it is. I'm trying to help you to understand, by the way, you do not have to break it down like this when you do these problems unless you would really prefer. So what is the 88% of 4 centimeters? Should be like 0.35 something?
3.5.
Exactly?
Or 3.51. Or 3.52, sorry.
There we go. 3.52 centimeters. So what does that say? That says, if I do this, it's going to go up and down once in 0.46 seconds. It's going to go up and down twice in 0.92 seconds. It's going to go up and down another time in 1.38, then another 0.46. And I'm going to be left off with about 0.16 seconds left when I'm sitting right here after the 4th time. 0.16 is more than a 4th. So it's going to, a little more than a 4th. So it's going to go up to the top. It's going to have a touch left, so it's going to be on the way down, but not very far. So is it 88% of the way up to positive side? Exactly right. Now let's say I did all this and then there was another part to the problem and I literally said, hey, now tell me where it is in 3 seconds. Okay? Just so we understand ourselves, what would you have to change about this and what wouldn't you?
Just go back to the sine and multiply it by 3 instead of...
All of these constants are set, exactly. The constants are constant to the scenario. So the only thing you'd have to do is put a 3 here. What if instead I changed this? What if I still kept it at 2 seconds, but instead of poking it up at the very beginning, I poked it down at the very beginning? It's negative sign, which in turn would just mean we would get a negative answer. But doesn't that make sense? If that amount of time going up would put us in the positive side of things right up here at 3.52 centimeters, doesn't it make sense that if I poke it down, it would go 1, 2, 3, 4, and in a little bit extra go quarter and just be the exact same way, just in the negative direction? Yeah, and that's what the math is. Perfect time. All right. Hopefully, oh, I need to finish my, for those people that struggle on this, I need to finish this right over here. And this is like this is what I do on these problems. Find K, find T, find frequency / angular frequency. And again, sometimes you can skip straight there. Then you do your, I'm going to make this generic. You know that it doesn't have to be cosine. It can be sine or negative cosine or negative sine. What decides cosine, sine, negative sine, all that sort of stuff? Yeah, initial position. For anybody that cares, in case you have seen it, there is an addition to this equation that accounts for this. It's, hey, great, what if Spainhour, it's not at one of those nice 4 positions? What if it's not up here? What if it's not here and poked one of those ways? What if you go up some amplitude and then flick it? Well, now it's not starting at the max amplitude. It's somewhere in the middle. And what you have in that particular case, which you may know from pre-calculus, is phase angle. Okay? Phase angle is literally just adding essentially an angle to say, hey, we started 12% of the way through this cycle, as opposed to we started at a nice 0 or 25 or 50 or 75. That's all phase angle actually is. Now, we are not going to worry about that on the math in here. That is just kind of, if somebody has seen it before, great. So don't worry if you're like, I've never seen that before and I don't care. Awesome. Leave it alone. You don't have to touch it. I just want to drop that kind of brief conversation on phase angle for two reasons. One, if you've seen it before, and two, if you're coming to physics 2, you're going to want to know what phase angle is. All right. So there's your steps right there. There's your very quick generic steps. And what about this changes if it's a pendulum as opposed to a mass spring system?
Well, your formula to get the period.
Yeah. And therefore, you just don't have to get K, right? You don't have to get K for a period. You saw that at the very beginning of the day. All you needed to get the period was the length. That was it. So if you were given a pendulum, basically skip K and go on from there. Questions, concerns? Will be easy. All right. I'm skipping to the second half of this. I apologize for going so quickly through this information. It's helpful for the AP test. It is also very helpful for coming into physics 2, which is why I pushed so hard at this particular point in time, but I do understand how annoying that is. So we're going to shift off of simple harmonic motion, sort of, and start talking about waves. It's like I had to set up ahead of time. All right.
I remember SHM propane.
That was fun.
It was 100%.
And you're supposed to be doing a lap.
Okay, now I am going to cover in about 2 and 20%, 2 and 20% days what when I was in college was an entire semester. Okay, so to put that in perspective, this class that you're taking now is also a semester in college. So all of this information that you've gained this year is a semester, and then I took another semester just for waves. So there's obviously going to be a learning curve here. So today all I'm going to do is start talking about kind of the difference of waves and some very, very generic vocabulary, which I know hopefully most of you actually already written down. Okay, if you haven't, no judgment there. It was not meant to be condescending or anything sort of thing. But I kind of want to just give you a visual representation. Apologies for online. Let's see if I can't very quickly because I don't want to waste too much time. I thought there was a thing I could do. Is it that? No, maybe. Do a thing. Do a thing. Oh, maybe. We stand a chance. Hey, everybody. All right, so you guys are going to be on a future video. Oh, look at that. Look at that. Look at that. Look at that. Look at that.
Can you stand in front of the camera?
Okay.
What else would you're gonna live forever? It's like right in front of the camera.
No, you were really close to the
All right.
We're gonna be on
So-
15 hours YouTube.
So we have, there it is. So we're talking about the spring right here. Now, a wave is this. Okay, hold on. A wave is that. Now, what you'll notice about this is that it appears like something is moving, right? You can see something moving. But if you pay very close attention to any location on this spring, which is why there are these like black things that I've put on here, they don't actually go anywhere. They don't go anywhere at all. And I mean, that's not true. They do wiggle back and forth. But are they what's actually traveling that you're looking at?
No.
No. You can see what I'm doing right now. You can kind of like watch this thing. Technically, if somebody was fast enough, you're not. We could measure its velocity. We can measure the velocity of this thing, which have you run next to it and see, well, shoot, I mean, we don't even need you to run next to it. We can do a very simple thing right now. Okay, somebody got a timer. Okay, go ahead and start the timer when the disturbance is here the first time, and stop this timer when it gets back here the second time. Okay, ready? So you don't have to do it right away. Just let it go to let it kind of bounce the first time, and then when it comes back and hits, that'll start it, and it hits back again. So here we go. And now, and now. What'd you get?
1.25.
1.25.
23.
So right in a little bit above 1 in that particular chain. What's the only other piece of information we have to calculate its velocity? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 37. So it went 37 one way, which means it went 72 feet in total the other way. So 72 feet divided by, let's go, 1.2. What you got?
72 divided by 1.2.
It's about 60 feet a second. Okay, we're not used to feet per second, so go ahead and divide that by 3.28.
About 18.3 meters a second.
This thing goes about 18.3 meters a second. Now, what was it that's actually moving through the system? And the answer to that is energy. The disturbance itself is what's moving through the system. As a matter of fact, let me stop saying system and start doing vocabulary. The medium. Okay? The medium is the material through which a wave moves. For example, many of you have probably been to a sporting event like baseball or hockey or that type of thing in which they have performed the wave. Okay? The wave is not terribly scientific, but it does really help me make my point, so we are going to do the wave. You are going to give full participation, full send, or this is what we are going to be doing the rest of the year, and the test will still be on the same day. All right, ready? So we're going to start on this side, okay? We're going to go, the wave is going to start over at Anthony and head all the way over here to Courtney, okay? So in kind of a diagonal fashion. Full send, everybody. I will make you do this like 20 times if it's necessary, okay? So you get ready to go up. Full effort, maximum effort, and go.
You're late.
Some people didn't leave the seat, okay? Full effort, okay? I got maybe 70% effort on that. That's great. 100%. Maximum effort. Let's start over this side. We're reversing it. Side 40. And go. Your weight was very slow. It's fine. It's fine. Okay, now, important thing.
Oh my gosh, we're getting judged.
I point 100%.
You weigh.
100%.
Yeah, you
show
didn't
you how to
participate.
prop.
Yeah, you didn't do 100%.
Yeah, you just got
Can't wait to watch this
I
video.
feel like you watched that and you were just like, holy crap, I have never truly seen the wave before I saw that wave. Like, if you come to a game with me, I'm just
You are the
before
wave.
First 20 minutes. 20 minutes before the game. I'm just sitting out there outside just going.
You know what? You should call the wave.
That was good. That was good. Okay, I gotta work on my left elbow. Okay, stretch, don't hurt yourself. Okay, you're a really bad way to talk about pulling your hamstring.
You should
Pull
be
your hamstring.
Fredbird.
The wave. All right, now. So, the point of doing the dumb wave was this. I literally pointed the way I wanted the wave to go. I said, Anthony, over to Courtney. You can literally point in the direction of the wave. Did you guys move that direction?
No.
No, you moved up and down, bringing me to another vocab word. Okay, actually, I'm going to skip that vocab word. Let's do this one first. Okay, a pulse wave. A pulse wave is this. A single disturbance. A single disturbance, you saw me disturb it one time, okay, and it's now traveling through the system. That is considered a pulse wave, okay? On the counterpart of that, the exact opposite of a pulse wave is what's known as a periodic wave, okay? And in this particular case, the disturbance, instead of being singular, is continuous. Now, here's a very important thing about this. Now, you're going to notice some very interesting. You're going to notice some interesting properties specifically with a continuous wave. It's also known, we'll talk about this in 2 days' time, a standing wave. So meaning it appears to not be moving. But watch what happens over here if I move my hand differently. Okay, now, notice my hand going up and down real quick. Watch my hand. Guess what kind of motion my hand is in right now? Simple harmonic. And guess what? Every single one of these, like if you spotted this particular guy right here going up and down, I'm not doing a great job right now, but if it was continuously going up and down, guess how it's moving? Simple harmonic. Correct. It's simple harmonic motion. So pulse wave is, pulse wave is a single disturbance. Then there's periodic wave, which is just a continuous. Next, so those are kind of counterparts. So you kind of want to put them on one end of the spectrum or the other. Now, there are some weird instances where there's like sort of a both. We'll talk about that a little bit. Okay, next one, transverse versus longitudinal. So you'll notice that I have been making disturbances on the spring either this way, up and down. Okay, and I have been making them a little bit this way too. We can muscles like this, side to side. Both of those are considered transverse. Which way is the velocity of the wave going? There and back. So we can kind of say, like, if we talk about axes to make things a little bit easier, let's just say that that's the z axis, and I will be the x and y. So if I'm moving here, I'm moving on the y, and it's going in the z. If I go this way, it's moving in the x, and it's going in the z. In both cases, the medium is moving perpendicular to the wave, right? The parts of the spring are going up and down when the wave's going like this, or they're going side to side when it's going like this. Both of those are perpendicular. That's considered a transverse wave. So were you a transverse wave or not? The wave was going this way, and you went which way? So was it transverse?
Yeah.
Yes. Yes.
So-
Yeah.
I know we're asking this because the book uses it. Is propagation just like the way
Propagation.
the wave is that just the way the wave moves?
So a similar word, kind of a counterpart to propagation is just velocity. It's moving through a system. The reason we don't use the word velocity oftentimes instead of propagation is it's not a physical thing moving through. It's the disturbance moving through, propagating through that particular system. Okay, last one to cover. Stop getting ready early. I'm not done. I've got like 2 things to cover, and if the bell rings, I'm going to continue. So please stop it. I'm making this harder to get through. Next, last one, the opposite of transverse is longitudinal. Whereas the medium moves perpendicular to the wave, this is one in which it moves parallel to the wave. So here is a longitudinal pulse wave. It's kind of harder to spot, and actually it's starting to do transverse as well. Ideally, I would have this here. I'll see if I can make this tight enough that it doesn't move too much transverse real quick. And it's still going to do it a little bit. But I can physically feel it over here even if you can't see it very much. Okay? The best example of a longitudinal wave is sound. Spainhour is vibrating his molecules right over here. They're hitting these back and forth, and the molecules are moving like this. Is every single air molecule hitting? Is my molecules that are leaving me hitting all of you in the ears? No. Are the same molecules hitting any of you in the ears? No. I'm hitting this one, which is hitting this one, which is vibrating like this. They are longitudinal, otherwise known as a pressure wave. We will talk more about that.
I got the book.
I know. I'm taking video of I only like half hour.
Waves in the ocean, what are they? Longitudinal or
Yeah.
they're both.
Oh.